All right, my friends, let's take a look at section 11.2. It is called Techniques for Evaluating Limits. All right, and you already have some techniques for evaluating limits. You've got, graphing, and you've got making a table. And then we've kind of figured out that you can, as long as your graph is continuous, you can just treat it like a function value. So section 11.2 is my preferred method if possible. So it's where you just do it analytically or algebraically. I think you'll enjoy it. So method 1 is direct substitution. That is fancy for just plug it in. An example illustrating direct substitution would be the limit as x approaches 8 of the quantity 5 minus x squared. And when is direct substitution okay? It's when the function rule that you are using would be continuous at your function value. And I think we all know the graph of 5 minus x squared, parabola, opening downwards, shifted up 5. That sucker's continuous everywhere. So let's just plug that 8 right in. So if you did, you'd have 5 minus 8 squared, which I believe is negative 59. And so there you go. There's an example of direct substitution. You could have the limit as x approaches 8 of 1 over 5 minus x. So go ahead and consider that one. The limit as x approaches 8 of 1 over 8 minus x. And then the limit as x approaches 8 of 1 over the quantity 8 minus x squared. So go ahead and consider those. Some of these direct substitution makes sense and some of them it doesn't. So let's think graphically about 1 over 5 minus x. It is continuous everywhere but at 5. And since we're just plugging 8 in, we could totally just treat that like a function value. So that would end up being 1 over 5 minus 8. AKA negative 1/3. All right, but the limit as x approaches 8 of 1 over 8 minus x. Direct substitution cannot be applied here. The graph is discontinuous at 8. So instead you'd need to fall back on one of the methods that we had learned previously. Those will never go away completely, unfortunately. So you'd need to fall back on graphing, which is my preferred method, or t-tabling it out and plugging numbers in that are approaching 8 from the left and approaching 8 from the right. So that would be like 7.9, 7.99, 7.999, 8.1, 8.01, 8.001, or just graphing it. And so if you were to graph this, you'd find that this is a 1 over x graph that just got shifted horizontally to the right 8. And so remember, a 1 over x graph would shoot up on one side of the vertical asymptote and down on the other side of the vertical asymptote. And so in this case, it would make sense to say does not exist, because the left-sided limit at 8 is different than the right-sided limit at 8. And then just a note, in this case, we cannot use direct substitution. And one thing that's really nice about, direct substitution is math kind of tells you no for the most part when you shouldn't be using it. So, no in the form of undefined. Also a comment, the word undefined applies to function values. It really, for your answer for a limit value, it doesn't really apply. So we don't use the word undefined when it comes to limit values. Okay, so limit is x approaches 8 of 1 over 8 minus x quantity squared. This is a 1 over x squared graph, which if you remember from the last example, approaches the vertical asymptote moving upward on both sides. And it got shifted to the right 8. So it is discontinuous at 8. We can't use direct substitution but you could fall back on graphing or the numerical method. And you would say, I hope you would say that the answer is positive infinity. And then again, here we were not able to use direct substitution. Okay, so direct substitution is the first go-to move, and then here's some examples of when you can't use it. So now we're going to talk about some other methods that I prefer over graphing. So there's factoring and canceling. Another method here. So let me give you an example, some examples of that. If we had the limit as x approaches 3 of x squared minus 9 over x minus 3. So if you look at this situation, if you were to try direct substitution, math would kind of tell you no, because you'd get 0 over 0. And then just a note for 0 over 0, this in terms of limits is considered an indeterminate form. And let's talk about why. So indeterminate form means to be determined. We don't know yet. So some people look at that and be like, it's obviously 0, because you were told 0 divided by anything is 0. And some people would look at it and say, no, it's undefined. Because anything divided by 0 is undefined. And some folks would look at it and say it's equal to 1 because anything divided by itself is 1. But here's the problem. We don't even have things that are actually 0. We have numbers that are approaching 0. Remember, we're not actually talking about what happens right at 3. We're talking about what happens when you're infinitely close to 3. So you have a number on the bottom that is approaching 0. You have a number on the top that is approaching 0. It turns out, in this case, we're going to have the number on the top or the number on the bottom is approaching 0 6 times faster than the number on the top. So your answer in this case is going to end up being 6. So what's a way to get that 6? Well, remember in the last section I gave you a problem where once you factored it and canceled out the common factor, you could figure out where the hole is by plugging the answer in the remaining function. And that's why this one's called factoring and canceling. So this would be the same as the limit as x approaches 3 of x plus 3 times x minus 3 over x minus 3. Now, it's okay to cancel these out because we're not plugging 3 in. We're plugging anything but 3 in. And so this really would divide out to be 1. So then this would be equivalent to the limit as x approaches 3 of the factor that remains. Let x take on the value of 3. So now we fall back on direct substitution. Let x take on the value of 3. You get 3 plus 3, aka 6. So in this case, a number approaching 0 divided by another 1 ended up equaling 6. All right, my friends. Okay, so that's factoring and canceling. That's one of my favorites because I have sound effects for the canceling, you know, and stuff like that. So, let's see. Okay, before we move on to more techniques, let's actually do an example that should help you really understand what just happened here. So let's do example 1. For example 1, let's do part A. Actually, the directions are for you to graph. And then part A, let's give you f of x equals x squared minus 9 over x minus 3. And that is the problem that we just found the limit of, but go ahead and see what it looks like when you graph that. Pausing the video, what have you. Okay, so, and this is a review from in the past. There's a chance though, I've had quite a few students that this did not make sense back in chapter 2, but now that we're in chapter 11, you have a lot more math under your belt, stuff makes a little more sense. So we're gonna go ahead and factor the top and the bottom. Remember that the x minus 3's did cancel as long as x was not equal to 3. And so you'd have f of x is equal to simply the line graph x plus 3, except right at 3. So when you graph this, you have just a line graph, y-intercept of 3, slope of 1. I did make my scale kind of funny, but this would kind of be a slope of 1. And so it would be this line graph except right at x equaling 3. So you'd have a little infinitely small hole. Oh my goodness. Please no one show my videos to Mr. Chase. He would just like die just a little bit when he watches me graph lines. Okay. There we go. Okay, so this would be the graph of f. And then I hope it makes sense that it correlates with what we were saying over here with the factoring and canceling technique, that if you cancel out the x minus 3's and then take the target value and plug it into the function rule that's left, really what you were finding is the coordinates of that hole. The hole or removable discontinuity is at 3, 6. And so that's what we were finding here. So as you get infinitely close to plugging in 3, you get infinitely close to a y value of 6. So the coordinates of that hole are at 3, 6. Okay, part B, just to check and see how well you are really understanding. Let's say I ask you to, let's see, graph. Actually, let's have you, graph. Okay, sorry. F of x equals 2e to the x minus x e to the x over x minus 2. Okay. A little challenge for you. So assuming that you've given this a try on your own, I'm going to go ahead and demonstrate factoring out the common factor on the top. E to the x, I hope, is obviously a common factor. I'm also going to factor out a -1 because I want to have positive x minus 2, just like the bottom. So I'm going to actually factor out negative e to the x. And then negative e to the x times positive x would give me this term, and negative e to the x times -2 would give me this term right here. And then the x minus 2's cancel as long as you're not plugging in 2. So we'll just go ahead and say, so f of x is simply the graph of -1 times e to the x, except right at the little instant where x is 2. So graphing this, don't even need that, do I? I'm going to make these closer. Okay, 2, -2, let's see, 3, 6. Okay, so let's graph f of x equals -e to the x. If I was to plug in 0 for x, I'd have e to the 0, which is 1, but then times -1. Oh. 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 All right. 1, 2, 3. Okay, -1. Putting in 1 for x would give us -e, which is almost -3. Putting in -1 for x would give us 1 over e, or -1 over e, that is. So it's like kind of like -1/3. And so this would be the graph. Now let's think, if you were to plug 2 into this function, you would have had e squared. So a number a little less than 3 squared would be a number somewhat less than 9, probably quite a bit less than 9, to be honest with you. So at 2, I'm going to put a hole right there. So the graph basically looks like the graph of e to the -x, or negative e to the x. And it acts just like that, except that little instant where x is 2. So I'm going to label the coordinates of this removable discontinuity as 2 and think, what would the y coordinate be? So that little removable discontinuity, the y coordinate would be negative e squared. So just plugging it into the function value after you'd canceled that out. Okay, and then for part C, let's have you evaluate the limit as x approaches 2 of 2e to the x minus x e to the x over x minus 2. You could do it from your picture and say the answer is negative e squared, or, and I'm going to emphasize notation here, we write this expression, the limit as x approaches 2, until you finally let x take on the value of 2, or until you let x, until you evaluate what happens when x gets infinitely close to 2. So watch my notation, because I'm going to be watching for yours when I test you. So we're going to write the limit as x approaches 2 of, I'm going to factor out negative e to the x just like we did before. I'd have x minus 2 as the other factor. I can cancel these out because we're not letting x attain 2, we're letting x take on values infinitely close to 2, so these really would divide out and be 1. So I can still say equals. I'm still writing the limit as x approaches 2. Now in the next step, I'm going to finally plug 2 in, which is why I stopped writing the limit statement. You write the limit statement until you let x take on the value 2 or take on values infinitely close to 2. So watch that notation because I'll be looking for it. There we go. All right, my friends, and hopefully you can see the relationship between the factoring canceling technique and things you were told about graphing anyway. I've had students not understand the whole idea or the removable discontinuity idea from back in Algebra 2 until we finally throw in the calculus this year, and then all of a sudden things make a lot more sense. Okay, let's do, okay, let's talk about the next technique. I call the next technique the conjugate move. So an example illustrating the conjugate move would be the limit as x approaches 0 of the square root of 7 minus x minus the square root of 7 all over x. Okay, so first let's talk about why my favorite move is not going to work here. Just plugging 0 in. So unfortunately this graph is discontinuous at 0. You can see that evidence with the x on the bottom there. Also, math will tell you no if you try. So let's just show what happens if you try direct substitution. You get the square root of 7 minus the square root of 7 over 0, which is equal to, dun dun, 0 over 0. And what do we call 0 over 0 in a limit statement? Since you don't have exactly 0 over exactly 0, you have a number approaching 0 over a different number approaching 0. This, my friends, is called an indeterminate form. You're going to want to have that vocab when you go into Calc BC. Okay, so I hope you can see here that factoring and canceling is really not an option with the way things look. And so that's where, in this case, we'll be rationalizing the numerator by multiplying by a creative version of 1 where we use the conjugate of this expression. So we would say that this equals, that's right, you're going to write the limit as x approaches 0 again. You're going to rewrite the function rule as is, but then we are going to multiply by a creative version of 1, where we take the piece here that has square roots in it, and we just flip the sign. And you'd have to multiply by that over itself, because we're trying to multiply by what number? We're trying to multiply by 1, so that we're just changing the cosmetics. We're just changing the way it looks, not its true value. So, so writing the limit statement again, limit as x approaches 0, and then let's multiply the top out. So if you multiply square root 7x by itself, you get 7x. Now watch this, your outer product, square root 7x times square root 7 is what it is. But its opposite is right here on the inner product to cancel out. So it's just lovely because it just goes away. And then your last, when you multiply those out, you'd have minus 7. Now on the bottom, please do not distribute the bottom out. Please leave it factored. If you distribute it in, you'll just have to factor it right back out. Because look what's going to happen on the top. The 7s vanish, and you're left with negative x. And now the x's cancel. See why you're glad you left the bottom factored now. So let the x's cancel. Yes, you're writing the limit statement again. Okay, now that we canceled the x's out, I would say we probably canceled our indeterminate form problem out, because notice it would have been 0 over 0 if we tried to plug in the target number. So once you get that to cancel out, with or without sound effects, totally up to you and how exciting you want your life to be, then I would go ahead and try direct substitution again and see if the math tells you that it's okay. So let's let x take on the value of 0 and see what we get. We'd get negative 1 over the square root of 7 plus another square root of 7, also known as negative 1 over 2 square root 7s. You could leave it like that, or if you can't stand it, you need to rationalize the denominator. You could always multiply it by square root 7 over itself, and then you'd have negative square root 7 over 14. And that's a super pretty little answer there. So this time 0 divided by 0 ended up being negative square root 7 over 14. All right, just kidding. It wasn't really 0 over 0. It was like a number approaching 0 divided by another number approaching 0. Okay, so that is an example of the conjugate move. Another example of the conjugate move would be something along the lines of the limit as x approaches pi over 2 of 1 minus sine of x over cosine of x. So notice if we try direct substitution, you get 1 minus 1, which is 0, divided by cosine of pi over 2 is also 0. So you get, what's it called? Good, an indeterminate form. Very good. Okay. And you don't have a ton of room for factoring and canceling. And so let's play with the conjugate move. The only thing that could potentially have a conjugate would be this top part. So let's say this would equal the limit as x approaches pi over 2. You're writing the limit statement, right? Don't make me come over there. No, just kidding. You're writing the limit statement, right? Okay, so we'd have the function rule as is. And then what's the creative version of 1 that would help me get basically I'm trying to get a difference of 2 squares pattern on the top. So that's why you multiply by the conjugate. Okay, now which one should I distribute? The numerator in this case or the denominator? It would be the part where you chose the conjugate for it. So let's multiply it out. We'd have 1 plus sine of x minus sine of x, so it vanishes, and then minus sine squared x. Over, and then we are not going to distribute the cosine x in the bottom. Okay, now fight the urge to refactor this and cancel it, because you'll just end up back where you were in the first place. Instead, look at this numerator, trig function squared. We're going to reach for which types of identities? Oh yeah, Pythagorean identities. So now we have the limit as x approaches pi over 2 of cosine squared x over cosine x times 1 plus sine of x, and with or without sound effects, up to you, one of the cosines cancels. So, all right, so now we're left with, all right, the limit as x approaches pi over 2 of cosine of x over 1 plus sine of x. Okay, And it doesn't look like much happened if you look at what I've got compared to what I had. Like, it kind of looks like much ado about nothing. But let's see what happens when we try again. Let's see if we got rid of that indeterminate form. Let x approach pi over 2, cosine of pi over 2, 0. Sine of pi over 2 is 0, so you'd have 1 plus 0 on the bottom. So you have 0 divided by 1, which is 0. There you go. All right, my friends. Okay, so that is what I have to say, I believe, about the conjugate move. So let's talk about another method. So another method would be for you to just basically do what you can to simplify. So this is kind of a broad category, but here's an example that could fall under that category. The limit as x approaches 0 of 1 over 4 minus x minus 1/4 over x. Okay, direct substitution, always consider it. You'd end up with 1/4 minus 1/4, which is 0 divided by 0, an indeterminate form. Indeterminate form means to be determined or try something else. I hope you can see here the conjugate move or factoring and canceling, not so hot. So instead, I would encourage you to simplify a big mess like this. So that would mean get rid of the compound fraction, fractions within fractions, no bueno. So instead, let's get common denominator up here on the top. So that would look like multiplying 1 over 4 minus x by 4 over 4, taking the 1/4 and multiplying it by 4 minus x over 4 minus x. And then it's all over x, like so. So let's see what we now have. We have the limit as x approaches 0. You're writing your limit statements? I hope so. You want it to become muscle memory. Multiply on the top, you'd have 4, and then treat this like a -1 right here and distribute it in. So you'd have 4 minus 4 plus x over 4 minus x times 4, and then all of that is over x. Okay, so then now this is equal to the limit as x approaches 0. On the top, the 4's vanish, and so you just have x. On the bottom, you're dividing by x over 1. Now that we have just one fraction on the top, I'm gonna flip and multiply. So I'm gonna multiply by 1 over x. All right, my friends. Heads up, in Calc BC, if I call on you and you help me cancel stuff, I'm gonna wanna know what your sound effects are. So it's time to get comfortable with whatever your sound effects are. You know you've got them. Okay, so whatever, I don't know, but I'm gonna wanna know what your sound effects are. All right, so you'd have the limit as x approaches 0 of 1 over, you can distribute the 4 in or not. It really won't matter, and you'll see why in just a second. So let's try direct substitution again. You probably got rid of your indeterminate form issue here. So let x approach 0, and you'd be left with 1 over 4 times 4, or 16. There we go. Okay. Last method. So I try to do these in order of things you should always kind of consider when you look at a limit problem. So the last method is to look at left and right. I guess I should put little hyphens here. Right-sided limits using a graph or a t-table, which is why, so this is kind of your last resort, or maybe you really like that a lot, so maybe for you it's not your last resort, but for most people they would consider that to be kind of a last resort. So if any of the tricks that I mentioned today do not apply very well, then this would be your last thing to try, okay? You should always be able to get the answers from this if the other things fail. So a quick example for that. if I asked you what is the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2, then how would you go about that? So a lot of people want to cancel those x minus 2's. I do too. The sound effects are calling. But the absolute value marks make it so that you can't. So because the absolute value marks would make the top be positive even if the expression on the bottom was negative. So you can't always cancel that out. So instead you're left with, the methods that I mentioned in notes today don't apply. So instead you're left with looking at left and right-sided limits using a graph or a t-table. And so I'm going to go ahead and show it in graphing form, but I'm going to use a t-table in my head to demonstrate or to get the answers that I'm going to graph. Okay, so direct substitution doesn't work because you get 0 over 0. Okay, which is indeterminate. Okay, so the number in question is 2. So let's just plug in some numbers and see what happens. So if I plug in 1 for x, I'd get 1 minus 2, which is negative 1. Absolute value that, you get positive 1. If I plug in 0 for x, I'd get 0 minus 2, which is negative 2, but you absolute value makes it positive 2, and then it's divided by negative 2. Wait, did I do that wrong? Plugging in 1. Oh, sorry guys. Plugging in 1, you get negative 1, and plugging in 0, you also get negative 1. And so what if you plugged in something really close to 2, like 1.999999, You'd have 1.9999 minus 2, which is negative, but then it makes it be positive, and then you'd have its negative opposite down here. And so, so you end up with everything, any number that you plug in to the left of 2 would have given you a positive 1. And then if you plug in things like 3, 4, 5, then the absolute value marks are totally redundant. And so you end up with positive 1 for anything bigger than 2. Look at that. Wow. So based on this picture, what would we say, based on this picture, what would we say the limit as x approaches 2 from the left of this expression is? I hope you would say it's negative 1. And what's the limit as x approaches 2 from the right of this expression? It's 1. And so because the left and right-sided limits are 2 different things, we would say that the double-sided limit, which is the limit as x approaches 2 of this expression, does not exist. But notice that for this problem, none of the other techniques I talked about would really be applicable, so you would fall back on what you learned in section 11.1, which is looking at left and right-sided limits. All right, my friends, last example. Okay. Mom, what game are you guys playing? Mom? Mom? What game are you guys playing? What game are you guys playing? Sorry. Okay. Okay, so my son is 5 and he is a very sore loser. So if you are hearing shrieking and weeping and gnashing of teeth in the background, it's because he's probably losing it. Sorry. All right, last example, example 2, evaluate this limit, that limit expression for each given function. So part A, let's say I give you f of x equals x squared minus 7. Okay, I'm going to do a little more writing than what we would really have to do, but I hope it makes sense. So we're trying to figure out what does this expression equal for this particular expression if f of x is defined as x squared minus 7. So I'm going to go ahead and rewrite this limit expression. So the limit as h goes to 0 of f of x plus h minus f of x all over h. You probably recognize this beast as the difference quotient that we have tortured you with from time to time, probably starting in algebra 2. So this would be equivalent to the limit as h approaches 0 of f of the quantity x plus h would be the quantity x plus h squared minus 7, and then minus the entire f of x expression. So this is f of x plus h, this is minus f of x, and then it's all over h. So this then is equal to the limit as h goes to 0. Let's expand this out. X squared plus 2xh plus h squared minus 7. Distribute the negative. Okay, the 7's vanish, the x squareds vanish. So I'll just go ahead and like show that they're goners. And then notice that we still have this limit expression. On the top, the h would factor out. You'd have 2x plus h up there over h. And then until now, we would have gotten an indeterminate form. But once these h's cancel, then you should be able to let the remaining h's go to 0 and get an expression for your answer. So let that h go to 0 and you'd have 2x. So your answer is 2x. All right, my friends. So we're looking at the difference quotient problems now mixed in with a little bit of limit work. You'll see why soon enough if you're not sure. Okay, part B. Let's see if I can fit it over here. All right, same expression up here, but this time f of x is defined as 1 over x. Good time to pause the video and see if you can do it without me. But I'm going to go ahead and show as many steps as I did before. So starting with the limit as h goes to 0 of f of the quantity x plus h minus f of x all over h. Then, still writing the limit expression, we're going to write it until we finally let h take on the value of 0 like we did here. So limit expression, and then let's figure out what's f of the quantity x plus h. It's 1 over the quantity x plus h minus f of x, which is 1 over x, all over h. Common denominator on the top, this falls under the category of simplify. So we're going to have, we're going to multiply this fraction by x over x. So we'd have x over x times x plus h minus, we're going to multiply this fraction by x plus h over itself. And it's all over h. So we now have the limit as h goes to 0 of x minus x is 0, but then you have negative h on the top. You're dividing this entire fraction by h, which is equivalent to multiplying by 1 over h. The h's cancel. And once those h's cancel out, you should be able to let the remaining h's take on the value of 0, and whatever you have should be your answer. So let this h take on a value of 0, and you'd have negative 1 over x squared. There we go. Notation, limit statement, limit statement, limit statement, limit statement, limit statement, and then I quit because I finally let h take on the value of 0. Watch your notation, I'll be looking for it. All right, my friends, I hope this is helpful. At least this video is shorter than the last one. Take care, everybody.